chloric acid, sulfuric acid, and nitric acid. Know the name and formula. Also, if you can, learn the formula for ethanoic acid as well. The thing about the ones at the top here is these are the strong acids, and we'll define that in a second. And the one underneath here is an example of a weak acid. And those of you doing triple know that that is a carboxylic acid, which are weak acids. The thing about strong acids is they fully ionize. If you put them into water, they completely break apart to give H plus and the anion. So it's always going to be a 1- ion if you've lost one H plus. And so that's true for nitric acid, loses one H plus and you're left with a nitrate ion. You need to know the formula of the nitrate ion well. So NO3 and then minus a nitrate ion. Sulfuric acid is a bit of a strange one because it's got two H's, both of which can be lost. This is something that people often get wrong, is that it produces 2 times hydrogen ions, not H2 plus, but 2 lots of H plus, and you get the sulfate ion. So make sure you know the formula of the sulfate ion as well. So think about these, and think about all strong acids by definition, is they fully ionize. I've always taught the word dissociate, but the exam board liked the word ionize. Either would be okay though. Fully ionize to release H plus. 1 mark for saying acids release H plus, 1 mark for saying they fully ionize. Weak acids do the same as strong acids in that they ionize, and it's this H that's lost. You're still left with an H plus, and you end up with what we call the ethanoate ion, in this case ethanoate. This is a weak acid, and we say that weak acids partially ionize, partially dissociate. It's good that we use the word ionize rather than dissociate because it's easier to spell as well. So make sure you know the formula of the acids and what they break apart to, and know the definition of a strong acid, fully ionized to release H+, and a weak acid, partially ionized to release H+. Then you need to know the reactions of acids. And there are essentially 4 reactions you need to know, and we'll look at each of them in turn. The first of which is really from the redox topic, which is all part of chemical changes in paper 1, but it's the reaction that we sometimes call MASH, which is that metal plus acid, and it'll be a reactive metal, one high on the reactivity series like magnesium, will react with an acid like HCl to give a salt, in this case magnesium chloride, and hydrogen, which is H2. I'm going to talk about this in a bit of detail because people slip up on this. First thing you need to remember that is an issue is that lots of students forget that H2 is the formula of elemental hydrogen, and that's what you produce here. The next thing to highlight is you need to be able to work out the formula of the salt you're producing. So it comes from magnesium, which here of course is just the metal, but here is a 2+ ion, and here you've got chloride, which is a 1- ion, and therefore to balance it you need 2 HCl. We know magnesium, by the way, is 2+ because it's in group 2. It loses 2 electrons when it forms an ion, and we know chloride is in group 7, so it must be a 1- ion. Because that's 2+, and each of these are 1-, it must be that you have 2 chlorides for every 1 magnesium to make it overall neutral. So you need to work that out rather than guess the formula, and then you can balance it correctly. And that's what people struggle with. So we're going to practice that in class now. So I want you to work out the balanced equation for calcium plus sulfuric acid, and a reaction which you mustn't do because it will blow your head off, for potassium going into nitric acid. An explosion, what would you get in that case? Okay, so well done. Because calcium is 2+ and sulfate is 2-, that must be the equation for the first one. No need to balance it. Potassium is 1+ and nitrate is 1-, so that's the formula of the salt. Because that's H2 there, to balance it we can either put half H2 or put a 2 there, and there to balance it. You need to be able to work those things out in an exam from what you know. Now, the thing to realise with this particular reaction is that it's a redox reaction. In other words, the magnesium is going from magnesium to magnesium 2 plus, and that the hydrogen is going from H plus to H2. Now we have to recognise which one of those is oxidation and reduction, and be able to balance those half equations, ideally, if we're really pushing the top marks. So have a go at that, and then I'll go through it. The top one, you've got one magnesium on both sides, and so you just put 2 electrons on the more positive side. For the bottom one, it's a bit harder because you've got two hydrogen atoms in H2, so we must need 2 hydrogen ions, each of which needs an electron to turn into hydrogen. So they're the 2 half equations. Magnesium is losing electrons, so it's oxidation, and the hydrogen ions are gaining electrons, so it's reduction. So overall it's a redox reaction, Right, so that's the first reaction of metals with acids, and the next reaction of acids are the neutralization reactions, and I'll come to the practical skills in a sec. So the first of which could be any metal oxide. So I'm going to use magnesium oxide, but it could be the one you did in class, calcium oxide, or any other oxide. It could be rubidium oxide, or copper oxide, or it doesn't matter, any oxide you like, and you react that with an acid, and it doesn't matter what the acid is either, but let's say sulfuric acid, and you always get a salt, in this case magnesium sulfate, and what you're left with, of course, is the hydrogens from here and the oxygen from here, so you're left with water. So for the neutralizations, you get water. There's no transfer of electrons here. You just end up with water from the H plus is from the acids, and the O from the oxide. Let's do copper oxide, which I think was probably the one we did in class, but let's do it with nitric acid for a change. The formula of copper nitrate, copper's 2 plus, and nitrate is 1 minus, so we need 2 of those. You always get water. To balance it, you need the 2 there. So neutralization reactions, metal oxide plus acid goes to salt plus water. That's one of them. The next one would be metal hydroxide, and that's nearly always group 1 metal oxide. So I'm just going to do one example, but it could be sodium hydroxide, lithium hydroxide, potassium hydroxide with any of the acids. And I'm going to use HCl here as a simple example. To give salt plus water, again to balance it. Well, it is balanced, isn't it? Already dead straightforward. So again, metal hydroxide plus acid goes to salt plus water. It could be any hydroxide, any acid, so that's the second type. The third one is slightly different. So the third type is the metal carbonates. I'm only going to use one example here again, but it could be any of them. It could be, for example, calcium carbonate, but it could be copper carbonate that we probably did in class, or potassium carbonate, sodium carbonate, plus an acid, let's say HCl this time. And again, you get a salt every time, and the formula is calcium chloride is just like before, calcium's 2 plus, chloride's 1 minus, it's that. Plus water again. The difference this time, and the thing that people often forget, is you get carbon dioxide produced. So whenever you see carbonate, the name should give it away. So carbonate gives you carbon dioxide, and so you see fizzing. So that's evidence of that reaction taking place. It's a good chance to remind you for paper 2 that you need to know the test for carbon dioxide as well, just bubbling through lime water. So just need to balance that equation by putting a 2 there. So they're the 3 kind of neutralization reactions you need to know. But I'm going to highlight a key point as well here, that for the neutralization reaction that you see here, you might be asked to write that as an ionic equation. So all that's going on there is that hydrogen ions from the acid will combine with the hydroxide ions from the sodium hydroxide or lithium hydroxide or potassium hydroxide and give water. So it doesn't matter what acid you use, or what hydroxide you use, the only thing that's really happening is this. All the other things are just swimming around in solution doing nothing. That's the reaction that takes place. And so that's the ionic equation, excuse me. That's the ionic equation. And it's worth knowing that. I've seen that quite a lot of times in papers for 1 mark. It's worth knowing that. So there are a couple of core practicals associated with this project. Required practical 1, which is the one that's probably asked the most in paper 1. There are 4 required practicals for triple for paper 1. So it's this one, titration, a couple others we'll look at. One of them is electrolysis, and the other one. And the last one is a temperature change one, which we'll look at in one of the revision sessions. Okay, so required practical 1 is either metal oxide or metal carbonate. So it's either, I'm just going to use a specific example, it's either copper oxide or copper carbonate, but it could be calcium carbonate, magnesium oxide. It doesn't matter what the metal is, it's either the metal oxide or the metal carbonate. And the key thing about those is they're insoluble, and you need to know that. And that's an important detail. So the whole point of required practical 1 is making a soluble salt from an insoluble base. Now the word base means something that can neutralize an acid, which is what we were just talking about on the previous page, right? So that's what bases are. Insoluble means it doesn't dissolve, but they do react with acids like HCl or H2SO4 to give a salt. This would be copper chloride, and this one would be copper sulfate. In both cases plus water, but the carbonate's got something different going on. That will of course produce carbon dioxide, and we'll see it fizz. So linking together the reactions we just looked at with the required practicals is an important idea. It's easy to not make that link if you're not careful. And let's just balance the equation as well, make sure it's right. Now with these I'm going to put the state symbols, and you should really put state symbols, get used to that. So the insoluble bases are solids, and the salts we're making are aqueous, water liquid, and of course carbon dioxide is a gas. So this is a good example where state symbols are important, because we're highlighting the fact that these are insoluble. Now that's important with the practical, because the first step for them both is add the metal oxide to the acid. The differences are, for the metal oxide, you have to heat it. So the differences are heat. So you heat the acid first, and then you stop heating it so it doesn't get too hot. So you get the acid nice and hot to almost boiling point, and then you start to add the copper oxide very slowly, bit at a time. The metal carbonate, you add it at room temperature, and the thing is about this one that it fizzes, as we've said already, and it's a much faster, easier reaction. You heat it up to speed up reaction, so increase rate of reaction. Again, paper 2 idea. So that's the difference between the two versions of required practical 1. We know this one's finished because it no longer dissolves. So you add a little tiny bit of the copper oxide and you see it dissolve in the solution. It just disappears because it's reacting. You could put reacts if you like. But really it's the fact that it doesn't disappears is the important thing. Whereas the copper carbonate, you know, that one's done because it stops fizzing when you've added enough. So you add it bit at a time, whoops, stops fizzing, until it stops fizzing. So different versions of the same practical. One's hot, one's cold, one stops dissolving, one stops fizzing. Then, the same for both of them, so you filter to remove the excess base. And then the next thing is the same, and this is the detail you need to evaporate half the solution, half the water, to increase concentration. And you do that, and this is the important thing people forget, over a hot water bath. Over a hot water bath. And what that would look like is something like so. So you heat a beaker of water over a Bunsen, and you've got your solution in there. Let's see that. Okay, so you heat a water bath. The water bath gets hot, the steam hits the bottom of the evaporating basin. The solution in the evaporating basin evaporates, and you remove about half the solution to increase the concentration. You know when you've done enough when it starts to get crystals forming around the outside, or if you dip a glass rod into it, crystals form on the outside. The reason you add an excess, by the way, of the base is to make sure all of the acid reacts. That's a detail that we should add as well. So you add an excess to use up all of the acid. Once you've concentrated it, you allow crystals to grow. So cool to allow crystals to grow. And that's the same for both of them, of course. And then you might just pat them dry once they've done. That's it. That's required practical one. That's a nice practical. You need to know all of those steps. And you do know them. You've done the practical a couple of times. You know it well. Just make sure you're ready to answer that next week. So required practical 2 is the titration. And let's think about why you might want to do this. So there's a number of reasons you might want to do it. One might be that you're trying to make a soluble salt from a soluble base, from an alkali. So it might be that you're trying to do the reaction between an alkali and an acid to make a salt, just like we did before. And so you can use titration for this. Okay, that might be one thing you're trying to do, and that comes up actually in the a method like this comes up in the resources topic for the Haber process. So you're making fertilizer using an acid and ammonia. It's a very similar process. It's exactly the same method. Or it might be you're just trying to make a salt, as I was saying, or it might be like in the quantitative topic for triple, you're doing a titration to work out the concentration of an unknown solution. We'll practice those calculations in a lesson when I've got you all here and in revision sessions after school and whatnot. Right, so it might be something like sodium hydroxide plus acid, HCl, goes to sodium chloride plus water. And you want to get exactly the right amount of each. Now, how would you know that you've got exactly the right amount of each unless you did a titration? Well, you don't. You haven't got, like with the metal oxide, you can't add an excess of one of them because you can't filter it off afterwards, and it doesn't stop fizzing because it doesn't fizz. So you have to do it using a titration. So what you might do is you might take one of the solutions and drop it into a burette. I'm just drawing them to remind you which round burette and pipette are. You won't have to draw them in an exam, but a burette looks like that with a little hole at the bottom. And think about a burette, it's very thin, it's got numbers on it, so you can do, you can work out the readings and whatnot. So you might put the acid in there, it doesn't matter which round you do it, and you might transfer into the conical flask using a volumetric pipette, or just a pipette will do, which looks something like that. Again, very thin, very accurate, and you transfer some solution. Let's say this is acid, and in here we've got sodium hydroxide. So you transfer a known quantity, a known volume, and a known concentration, maybe of the acid, of the alkali, into a conical flask. And the purpose of pipettes and burettes is they're very precise. In other words, you can measure to 2 decimal places, and they're very accurate. They're calibrated, so you know the numbers on them are right. You use a conical flask because you can swirl it well and mix the acid and alkali well, and you also have a special sort of indicator in there. You need to know a couple of indicators. So, phenolphthalein. Use phenolphthalein indicator, a special indicator that gives you a sharp colour change, or the other one might be methyl orange, and it'd be nice for you to know the colours. So an alkali, an acid, the methyl orange is red, and an alkali is yellow, and it's orange when it's changing colour. So that sharp colour change happens when it's neutralising. That's the end point when it's orange. The phenolphthalein, so the way to remember that, by the way, is that just like universal indicator, you know acid is red, and methyl orange is the same, and you know that orange comes from red and yellow mixed together, so that's how I remember that one. So just remember the red is just the same as universal indicator, which you know. The phenolphthalein is kind of the wrong way around, it's not what you expect. So the pink is when it's alkali, and it's colourless when acid. And so you had a few drops of indicator, and the key thing about those, and the word is sharp, they have a sharp colour change, rather than a gradual colour change with something like universal indicator. So you know when you've added exactly the right amount of acid to the alkali with your swirling. So a few drops of that into the conical flask, adding the solution of HCl, and you might do it multiple times. So if you're doing a titration to work out the concentration of an unknown solution of, say, HCl, you would do the titration once, you do it quite quickly, you do a rough titration. So you'd start with a rough one, and then you do a second and a third titration, which would be more accurate. And the whole point of doing those is you do them dropwise at the end point, or near the end point. So you know roughly where that end point is going to be because of the rough titration you've done. And you need to state in your answer about this that you measure the volume of acid through doing initial volume. So you measure the initial volume and final volume, you record those, and you do the final volume, take the initial volume, gives you the actual volume. So let's say it started at 0 and ends at 24.00, you've added 24.00, take away 0. You've got exactly 24.00 centimetres cubed added. So the final take away V initial equals V titer. That's the titer volume. And you need to state that in an exam, what you do there. So let's say you don't start it at exactly 0, you start it at, I don't know, 1.50 centimetres cubed, and it goes all the way up to 26.30 centimetres cubed. You can work out the volume of acid that's been added, which is 20, in this case 24.80 centimetres cubed, right? And always write the units. So that allows you to work out how much acid you've added. So that's what you might want to do if you're trying to work out the concentration. If you're trying to make a salt, like you would do, say, in the fertilizer practical, where you add ammonia to either sulfuric or nitric acid, or in the case of this one that we've talked about, making HCl, sodium chloride from HCl and sodium hydroxide, you can do one of two things. So you can either do the titration, work out the volume, and then do it all again without the indicator, because you don't want the indicator in there in the end, right? So you just repeat the whole thing without the indicator, knowing what volume to add. Or another neat way to do it is you can just chuck in a spoonful of charcoal, and that will soak up, that will react with, or it will bind to the indicator, and you can filter off the indicator sitting on the charcoal. So it's been pointed out my writing's dodgy, so rough titration there. Just to remind you, you can either, to make the salt, you can either add charcoal to get rid of, and then filter to get rid of the indicator that's in there, or do the whole process again without an indicator, knowing what volumes to add. And then you've ended up with a solution of the salt, and then to turn that into salt, again, you've got to do exactly the same as we did in the previous page, which is heat the solution over a water bath. And again, we've done that multiple times to point out that you have to do that. So heat it over a water bath, crystallize it basically. So I'm not going to go through all that again. A little detail to add with the titrations, of course, the volumes you've got here, we do, like with any scientific experiment, repeat to make sure we've got concordant data. We remove anomalies. We look out for that in the exam. So we might get given in the exam 3 volumes, one of them will probably be a volume that's nowhere near the other two, maybe a centimetre cubed or two away. We ignore the anomaly, we take the mean of the two that are close to each other, right? So look out for that. So using a pipette, using a burette, adding dropwise, using an indicator, final volume, initial volume, and do the crystallization at the end. And remember to remove anomalies and mean the data and give all the values to the right number of decimal places as asked in the question. Right, so there's lots to remember there. It's worth having a look at some practice questions. Right, so finally then a little bit on the pH scale. pH scale, you were taught in year 7 it goes from 1 to 7 to 14, which is only sort of partly true. What is true, that at pH 7, at 25 degrees at least, it's neutral. And so that means there are the same there are a little bit of hydrogen ions and hydroxide ions in solution, as we learned from the electrolysis topic, but the concentration of hydrogen ions and hydroxide ions when it's neutral are equal. So there's no more hydrogen ions than hydroxide ions. When it's alkali, you've got an excess of alkali, we get pH 14, and if it's pH below 7, we've got an excess concentration of H+, right? So that's what acid means. It means you've got more H+ in the solution than you have alkali, OH-. And the source of those is what we talked about right at the start of the session. We've got HCl or HNO3 or ethanoic acid or whatever. But the pH scale we need to know about. So let's think particularly about the pH scale going from 1 to 6. That's what we should think about, and that's where you're going to get asked questions about, really. We need to know that this is a negative logarithmic scale. You don't need to know what that term means. You need to know the idea, though, that as you increase the concentration of H+, the pH goes down. Don't forget that. You know it because you know that the more strong acids have low pH. You know that. You've known that since you were in year 7, or possibly even younger. So don't forget that in an exam. You know that the strong acids or very concentrated acids have low pH, where you've got a high concentration of H+, a low pH, right? But you also need to know it's logarithmic. So if you go from pH 2 to pH 1, that's a 10 times increase concentration of H+. So a 1 unit pH change is a 10 times change in H+. A 2 unit change, say from 4 to 2, is a 100 times increase in hydrogen ion concentration. And if you go from 6 to 3, let's say, that's 1,000 times increase in hydrogen ion concentration. So it's this logarithmic thing that's neither going up in factors of 10 rather than in steps of 1, right? So it's not twice as concentrated, it's 10 times. So there's this idea then that you can get strong acids. Strong acids will have a high concentration of H+ and therefore have a low pH. But weak acids, because there's very few of them in solution, are likely to have pHs around here somewhere. Weak acids only very partially dissociate. But you can have this unusual situation, just to finish this off. You could have, in theory, a weak acid that's quite concentrated, lots of, I'm going to call the acid HA just to make it simple. You could have lots of HA in solution and only one of which is dissociated, and that you give you a pH which is due to the concentration of that single H+ in there, because only one of them is dissociated because it's a weak acid. So that's a highly concentrated weak acid. We know it's weak because it's only partially dissociated, it's only partially ionized. Or you could have a strong acid which 100% dissociates or ionizes, such as HCl, so we'll call it HCl, and it might be that it's fully dissociated and also you've got 1 H+. So it's a very dilute, because only one in the pot, but it's a strong acid. And in that particular example here, the concentration of H+ is the same for both of them. So they might have equal, it's possible to get equal pH for a dilute strong acid and a concentrated weak acid, because you end up with the same concentration of hydrogen ions in there. That's a pretty good place to pause. A little tiny detail is you can do titrations, by the way, using a pH meter, and then you get pH. Well, you won't need to know what the graph looks like, but I have seen, you don't need to know this, but you might see something like that. That as you increase the volume of alkali, the pH jumps suddenly, and that's the point to which it's, that's the end point, that's the point at which it's changing pH. That's the volume when you've added enough alkali to neutralize all the acid. So it starts at a low pH in acid, I add alkali and the pH suddenly increases. An example of what that might look like is as an experiment would be something like that, where you've got a pH meter dipped into the solution, monitoring the pH as you add the acid, and you end up with that graph I've just described. All right.